The next part of section 10.1 is ellipses. Now with ellipses, the equations are going to be of one of two forms. It's kind of like parabolas. We're going to have a couple of forms, but these forms are going to be really, really similar. So we look at the ellipses, x minus h squared divided by a squared plus y minus k squared divided by b squared equals 1. And x minus h squared divided by b squared plus y minus k quantity squared divided by a squared equals 1. So the only really difference there is whether the a piece is under the x's or whether the b piece is under the x's. All right, so whether a or b is under the x squared piece or the y squared piece. And the reason why we use these two different equations instead of trying to do these as one is that this allows us to always let a be the bigger of the two numbers. By the way, in a real quick proof, you could say, well, what if a and b were exactly equal? Well, if a and b were exactly equal, what we would end up with is a circle. Let me show you that. So here's the equation. This one, obviously the a piece is under the x, but if a and b are equal, then we can replace this b here with letter a and set those equal. Now, what could we do to both sides? Well, we could take this left-hand side and the entire piece on the left-hand side and multiply it by a squared, and then obviously take the right-hand side of our equation and then multiply that by a squared. What would happen on the left is that the a squared here and here would cancel when I distributed this in. When I distributed into the other term, this a squared down here and this a squared would cancel. And so what would end up with what we would end up with on the left-hand side is an x minus h quantity squared plus y minus k quantity squared. So in other words, the denominators go away. And on the right-hand side of the equation, we just end up with a squared. Whoops, a squared. And if you notice, this is the exact equation we had for a circle, although we had our letter A as the letter R for radius. So if A and B were the same, then this would be a circle. So we're really only concerned with ellipses, what we call true ellipses, where the A and the B are different. That's why we have A greater than B here. So that's the idea. Now, the same types of things we're going to be looking for with ellipses that we looked for with circles and parabola. I don't mean the same exact characteristics, but the same overall idea. Now, as far as ellipses go, the part about ellipses, we have a center, we have a major axis and a minor axis. We have foci on the major axis, c units from the center, where c is the number you get by taking a squared minus b squared. And then we have something called the eccentricity, which is c over a. By the way, the c is, again, just a real number. We get it from a squared minus b squared. This is why we wanted to always have the a be bigger. Also, that allows us to call the major axis length 2a. So let me explain what I mean by those types of things. So what I've done is I've graphed an ellipse along the, in this window, I should say. So what I've done in green here is the actual ellipse. Now, you'll notice that in my case, underneath this ellipse, if you look really closely, I have a 5 squared underneath the x part and a 3 squared underneath the y part. So because 5 is bigger than 3, That's what we're going to call our major axis. It's the one that goes the length left and right because it is underneath the x part. And we call it the major axis quite simply because it's longer. So this blue line here, hopefully you can see that. If you can't, that's all right. This blue line, or I should say blue line segment here, that goes from -3, 1 out to the point 7, 1 is my major axis. Now the length of that, because we had 5 squared under the x part, the length of that from the center to the outside is 5 units, and from the center to the other side is 5 units. So we say the length of the major axis is 10 units, right? That was twice the value of our A. And then the minor axis is the shorter one. So we have here the minor axis. Again, it goes from 2, -2 to 2, 4. So its length is twice 3. Its length is 6. So that's the idea there. Obviously, our center here is at the point 2, 1. You can see it there. The other thing is these foci. We're going to have 2 focal points. Let's take a look at what that is for these 2 numbers. I just put them on, but let me explain how I got those. Remember, c squared is a squared minus b squared, or so take 25 minus 9, you get 16. C squared equals 16, so c would be 4 in this case. So if you move 4 units along the major axis to the left, you end up at the point -2, 1. If you move 4 units from the center on the major axis to the right, you end up with the other focus at 6, 1. So that's what those focus points or foci are, okay? Now the other unique thing about the focus is how it deals geometrically with points along this ellipse. So let me explain what I mean by that too. What I've done is I've created a triangle where the 2 foci are 2 points on the triangle, and the third point on the triangle is a point on the ellipse. And what I've done is I've done some things where I can use a slider to move that point on the ellipse to various places. It turns out that in each of these triangles, that the combined lengths of all 3 sides of this triangle are a fixed length. In other words, it's like we have a string here that is a single length, and we've tied it around all 3 points. And as I move that point on the ellipse, no matter what I'm doing, that triangle length is the same as that triangle in terms of the perimeter of this triangle here. Some people will eliminate this base length here, obviously, because it's always staying the same, and they'll say the distance from focus to a point plus the distance from a focus to a point on the ellipse. No matter what point on that ellipse is, that distance is always going to be a fixed value. So no matter how where I put that point on the ellipse, the distance, the combined sum from focus 1 to the point, and then from the point to focus 2, that combined sum is going to be fixed at all times. All right, so that is a property of these 2 foci. And then lastly, this eccentricity that I mentioned earlier. Well, that eccentricity is sort of how skewed the ellipse is. We'll talk about that more a little bit later, but I do want you to notice that it is C over A. Now, you can figure out which one of these is going to be bigger, the A or the C. Well, the A is always going to be bigger because A squared minus B squared equals C squared. So A, because we're subtracting something from it and getting a C, again, think of A squared and C squared are all just going to be positive. So you're going to take A squared, subtract something from it, and get C squared. So clearly the A squared is bigger than the C squared. So this eccentricity will always be less than 1 on the ellipse. So here's what I'd like you to do. I'd like you to take the standard form of an ellipse. Take this equation, find the center, the foci, the vertices, and eccentricity for this ellipse. Go ahead, push pause on the video and do that. So first off, let's start with the center. The center is fairly obvious because obviously it's the HK. So in this case, it's 3, 1. So the point 3, 1, whoops, 3, 1 is the center of this ellipse. Now, as far as the vertices go, well, the vertices, I may or may not have said this, I can't remember, but the vertices are actually these points on the endpoint of, they're the highest, lowest, leftmost, and rightmost. I put leftmost and rightmost on my ellipse. So in other words, they are the endpoints of the minor axis and the endpoints of the major axis. So if we look at our equation here, we have a 25 under the y part. So what that means is, and that's the bigger of the two numbers, 16 under the x part. So what that means is we're going to have to go 4 units from the center in the x direction, both left and right, and then 5 units in the y direction, up and down, in order to get my vertices. So we're going to have 4 vertices. The first, I'm going to have to do plus or minus, whoops, I thought I had that right, 4 onto the x value. And then we're going to have to, on the other 2 vertices, go plus or minus 5 onto the y value. All right, so we're going to end up with 4 total vertices. I'm going to put those in now. Hopefully you understand that why we're adding and subtracting 4 onto the x and why we're adding and subtracting 5 onto the y. Okay, by the way, the y is going to, these 2 vertices will be the endpoints of my major axis because we changed those by 5. And these 2 vertices will be the endpoints of my minor axis. So let me go ahead and do that. 3 plus 4 is 7. So we're going to get 7, 1 as one vertex. If I do 3 minus 4, I get negative 1, 1 as my other vertex, as my second vertex. Those are going to be, again, the endpoints of my minor axis. When you add and subtract 5 from 3, 1, adding 5 gives you a 6. And then subtracting 5 gives you a negative 4. So those are the, again, 2 endpoints of my minor axis, 2 endpoints of my major axis. Now, as far as the foci go, we have to figure out what that C value is. So maybe I'll just do it right here. So C squared is equal to A squared, which is in this case 25, minus b squared, which in this case is 16. Remember, the a has to be the larger of the two numbers. So c squared is equal to 9. That means c is equal to 3. All right. So c is equal to 3. Now, to get the foci, remember, I need to go 3 units, but I need to go along the major axis. So since the major axis, I am throwing in the y values. I should say, since on the major axis, we got those endpoints by adjusting y values. The major axis is going to be vertical. And so we're going to add and subtract numbers to the y values to get our foci. So we're going to take 3, 1, and then we're going to add and subtract. So 3, 1. We're going to add and subtract, whoops, 3 to the y values to get our foci in this case. If I add 3, you end up with 4, 3, 4. And if I subtract 3, what I do is I end up at a 3, negative 2. Eccentricity, well, that's a simple typing. That's just c over a. So in this case, c is 3 over a, which is 5. So the eccentricity is 3/5, which obviously is a number which is less than 1. By the way, we're always going to call c the positive root of whatever this number happens to be. So, and a is always going to be the positive root of whatever that number happens to be. So eccentricity is always going to be positive, but it's always going to be less than 1. So for ellipses, excuse me. Now let me graph all of those things so you just have an idea of what you're trying to look at. Tried to draw that out to scale here so that you can see its center is at 3, 1, and then you can see that this ellipse is stretched out further in the y direction, so up and down, more than it is stretched out in the x direction, left and right. The vertices are these points on the ellipse. And the foci, there's 2 foci. One of them, you go down on the major axis. The other one, you go up from the center on the major axis, and that's how you get to it. So there you go. That's the idea. So we've center, vertices, foci, eccentricity. So what I'd like you to do is I would like you to try to do the reverse. Let's find the equation of the ellipse where we know we have 2 vertices at 3, 1 and 3, 9. We know we have a minor axis length of 6. I want you to find the equation of the ellipse. Push pause on this video and then go and do the problem. This one's not too crazy. Hopefully you can figure this out. So we have vertices at 3, 1 and 3, 9. Now, those 2 vertices have the same x value, so we know that they're either on the minor axis or the major axis. Now, the minor and the major axis, whichever one we're on, 3, 1 and 3, 9, there is a length of 8 units between those 2 points. This says the minor axis has length 6. Therefore, these vertices must be the vertices at the ends of the major axis. All right, so the major axis must have these 2 as the vertices. And that means, well, we shouldn't be using this equation. That means that, whoops, that the a, the bigger number, is going to be under the y squared component. All right, hopefully, again, that's because I've changed in the y's. So there you go. So if the major axis has length of 8, that means that the A has to be 4. Let me write that there. If the minor axis has length of 6, that means that the B has to be 3. Remember, the length is double of what the actual A and B are. And then in order to find the center, which is the only other thing we need for this, we just have to find the midpoint of 3, 1 and 3, 9. So the center of those 2 points, it's, well, how do we get 1 and 9 halfway between? We've done this a number of times. Halfway between a number, halfway between 1 and 9 is going to be 5, right? So 3, 5 is the center of this ellipse. So we take this standard equation, center at 3, 5, length of the major axis is 4, so we're going to go 4 squared. Sometimes I'll just like to put 16. That's a little bit easier. Minor axis has length, did I say major axis has length of 8, A is 4. Minor axis has length of 6, that means B is 3, so B has to be 3. 3 squared therefore is 9, and that's what we get. So that's the equation that we were looking for. X minus 3 squared over 9 plus y minus 5 squared over 16 is equal to 1. Now, obviously things can get more complex. Like in this case, when we had to find the center and foci and vertices, we gave the equation in a standard form, but sometimes you have to complete the square, you move things around to make it look like this. I'm not going to do that because I did a lot of that in the parabola section. Same thing, I am going to do one where we don't just have vertices and minor axis length. What if we have this situation? We want to find the equation of the ellipse with the following properties. The center is at 0, 0. The focus is at 5, 0. And a vertex is at 6, 0. Go ahead and push pause and try to figure out what the A, B, the H, and the K are, and then fill in the equation. All right, so the H and K is pretty straightforward in this situation because H and K, it already gives us the center. H and K are both 0. All right, now the focus being at 5, 0, and the center being at 0, 0, the vertex being at 6, 0, tells me which is the major and which is the minor axis. Which of the two numbers, the number A versus number B is going to be underneath X and which is going to be underneath Y. Since the focus is changing the X value, I know that the major axis is going to be along the X values, and therefore the bigger number is going to be underneath the X. Hopefully that makes sense. And the smaller number, therefore, has to be underneath the Y. So that is the equation we're going to be using. We can copy that, throw that in here. H and K, I said, are both 0. Now, we go from the center to this vertex, 6, 0. That's again, we're changing in the X direction. So that A must be 6. So hopefully that makes sense. Along the x-axis, we have to go 6. Now, in order to find the B, that's where our focus comes in. All right. Remember, our equation to find the C that we have to add or subtract to one of the values of the center is C squared equals A squared minus B squared, when we're dealing with ellipses. So in this case, I know the c is 5 because that's what I'm given. So 5 squared equals, well, I know the a squared is going to have to be 6 squared because that's what I'm given. So if I need to find b, I can find it using this equation. All right. So we have now 25 equals 36 minus b squared. So b squared has to be 11. Now notice that's b squared. That is not b. B is the square root of 11. Um, I don't really need to even write the square root of 11 as b because the equation takes it as b squared anyways. But I'll write that for the sake of seeing that b is the square root of 11. So this is the equation we have with b equaling square root of 11, or b squared equals 11. A squared is 6 squared. I'm going to call that 36. X minus 0 squared. I'm going to just clean that up a little bit. I'm just going to call that x squared. Y minus 0 squared. I'm just going to call that y squared. So this is the equation, the simplified version of the standard equation of the ellipse we were describing. So there you go. That's how to deal with ellipses.